Hi everyone, my name's Saveen Reddy. I'm a group program manager in the big data team, and I work on Azure Data Lake. Today, I'm going to dive deep into Azure Data Lake Analytics and show you what actually happens when a USQL job is executed and what it means for you for performance. So, a USQL job in Azure Data Lake Analytics goes through, in a simplified form, 4 layers. First, it goes through our front end, where you submit the job. Then it is scheduled. And then it goes to our job manager, which distributes the pieces of the job to different nodes in our clusters. And then the final layer is what's actually running on each cluster, what's called a runtime. And each little piece of the job is called a vertex, and that runtime is responsible for executing that code. I know what I said may seem a little bit mysterious, but the rest of this session is going to drill into everything I said. So first, let's see what actually happens with a USQL job when you submit it. Well, it has to be compiled. Now, the compilation process is actually more complicated than you might imagine. It isn't just a simple compile into some managed code. In fact, if you look at a USQL script, what you'll see, it's actually divided into C++. Yeah, we generate C++, and we call the C++ compiler, and actually generate an unmanaged executable. And we do that instead of C#, so it can have the best performance. But of course, if you have to interrupt with C# code that you've brought with your own DLLs, we'll create a managed DLL also, so we can do that managed code interop. And then there are all sorts of other files. There's the algebra, which I'll show you a bit later. It's also called the job graph, and many other system files and runtime files. And all these files are called the job resources. And again, these are distributed to all the nodes that will run the job. And the nodes, again, are called vertexes. So this is a screenshot of Azure Data Lake tools for Visual Studio. Now, on the left, there are job properties. There's a whole host of them. And on the right, there's a big green blob. And the entire rest of this session is going to talk to you about what's on the left and especially what's on the right and what it all means. Let's start with the left. I'm focusing in on just 2 key points, 2 key properties of the job. At the very bottom is the vertices. So I wrote a USQL script and the USQL compiler and optimizer based on the script, what's happening in the script, and the data that it's seeing has basically said we can distribute this job or break it apart into 12,000 little pieces. Each piece is called a vertex. So we have 12,000 something vertices. Now, when I submitted the job, and this is not in the USQL script, it's actually when I submitted the job, I said I would like to pay for 1,000 units of parallelism. So if you had to think about the 2 numbers together, what I've said is for the 12,000 pieces of work, try to do, if you can, 1,000 of them at a time. And later on, we'll talk about the relationship of these 2 numbers and if we can actually guarantee that parallelism or not. And have I picked too high a number or too low a number? Now, the units of parallelism there, you saw I had 1,000. The units is actually called ADLAUs, which is Azure Data Lake Analytics Unit. And I will just sort of say usually nodes, but if the parallelism number is n, then you have n ADLAUs reserved for the entire lifetime of that job. Now, roughly speaking, an ADLAU is a VM with 2 cores and 6 gigabytes. So one thing I'd like you to keep in mind is in the future, we may actually have different kinds of nodes and give nodes, if your work needs less memory, we'll have a node that uses less memory. So we try to be more efficient. So this may not be true forever, but roughly speaking, this is true in the near future. Now, the USQL script I already mentioned is compiled, and I said these vertices, those are little squares, each one's a vertex. Now, the vertexes are grouped together. Right? They're grouped together based on the operation they're doing and on which part of the same data set they're on. So that grouping is called a super vertex or a stage. And you can see in the middle of this diagram here, we have 3 stages and all the work has been distributed into them. Now on the right, we're visualizing that graph, or that's actually called the algebra. The job graph is its visualization. That's the thing I'm going to show you in a demo a little bit further, and we'll look at the pieces and understand what they mean. But before we do that, let's just kind of back up and look at how vertexes run in this algebra or this job graph. So first of all, if I had asked for a parallelism of 1, meaning 1 ADLAU, that means reserve enough to do one thing at a time. And as you can see, the green here on the diagram on the left means those are vertices that are complete. The blue is a running vertex. There'll only be 1 blue vertex running during this job. So it's a serialized job. Now on the right, I've asked for a parallelism of 4. That means reserve 4 nodes, if possible, to do everything. Now, and in this case, we can see 4 are done and 4 are in progress. And I'll repeat this again. Just because I've asked for 4 nodes of parallelism, 4 add allows, it doesn't mean I'm going to guarantee all 4 can be used. And why that's the case we'll reveal a little bit later. Now one more thing, because these graphs look sort of serial in their own right, if a stage on top has a dependent stage on the bottom, it may be that the stage afterwards can still start running even when the stage before hasn't finished. So that's an example of 2 stages running in parallel. And notice the one on the right. The job is almost done, but there are 2 running vertices at the very last stage. Now if I had asked for 1,000 add allows, 1,000 nodes, obviously at the very last stage, 998 of them are not being used. So you have to be on watch for this, because you're wasting those nodes if they're not being used, right? Now let's take a look at the job graph, and we're going to look at a super vertex or a stage and get a little more detail on what's going on. So SV obviously means super vertex, and the next number 570, they're just already sort of randomly assigned numbers, so it doesn't have any specific meaning, just helps you identify the stage. Aggregate is telling you what's happening in the stage. In this case, it's probably doing an aggregate, like a group by, right? It's pushing some numbers together. And there's some other numbers underneath it that are quite interesting. Of the 12,000 pieces of work, 252 are in this stage. That means they're doing the same operation on different pieces of the same data set. On average, each vertex, or a vertex, took 2.45 minutes to run, right? So this is, if I could somehow magically allocate all the vertices to this stage, the entire stage would take about 2.54 minutes. Now, not all vertices are balanced like that. Some can take longer time, some can take less. This is the average time. Now, in total, this stage read for some files, and it read only about 4.3 billion rows, right? And it read 1.8 terabytes and wrote about 1.2 terabytes. So data in, data out are kind of balanced. Now, when you look through these big data systems, nodes fail. A vertex can be running on a machine, a VM can be running on a machine, and a router goes out, or a hard drive blows out. So the machine is going to have a problem. Maybe there's some other issue. Maybe there's a networking issue. So what does the system do in ADL analytics? Well, we know this vertex. We can run it again on the same machine, or we can run it again on another machine. But the key thing is, as a uSQL developer, you don't have to worry about it. Now in this stage, what you can see is the stage is fully green, and it would be red if it had failed, but it's fully green. That means the stage completed successfully. And there's a little yellow slice there. What that means is, hey, one of the vertices had a hiccup. So we reran the vertex and then it ran. And this is really critical for a big data system because, failures happen. And you rely on a system like ADL Analytics to sort of mask those failures for you, right? So you run on commodity hardware, which of course commodity hardware fails, but our system is designed to overcome those failures and hide them from you. They're shown here just so you know the process is in place and actually active. Now, let's take a look at an actual job. Let me start Visual Studio. Now, I have 2 jobs loaded. Let's take a look at the first one. And many of the screenshots I showed you are from this job. Let's look at the top. And I'm going to look here, and you can see it went through several phases: preparing, queued, running, finalizing. The running phase is quite interesting. It took about 40 minutes. That's how much I'd have to pay for 1,000 nodes for 40 minutes. I'll scroll down, and you can see the 1,000 nodes of parallelism, the 12,000 vertices, and it read about 11 terabytes and wrote about 10 terabytes. And of course, on the right is the graph. Now, remember all those vertices I talked about? Well, I had clicked on a button here called load, so now that's why it says reload. So all the information about the vertices have been contained. And of course, now I can sort of play it back, which you've seen in many of our demonstrations of Azure Data Lake tools for Visual Studio. But what I'd really like to focus on is this Diagnostics tab, which takes advantage of all that vertex information. I'm going to go to Resource Usage. Now again, we've shown this demo many times, so I'll remove the things that aren't important, and again, look at the blue line. It's how much I allocated, how much I'm going to pay for. The red line is how many are active, right? And there's a modeler here, so I can show, for example, hey, if I'd paid for 2,422, well, it would take much less time, but much more waste. But let's go back here and just think about this. Why did the graph go down here? Why was it able to go up here? These are performance questions because, hey, when this graph goes down here, it means very few, maybe even one vertex is running. So at that point in time, the job is serialized. So we want to understand why would that be the case. Clearly, it's going to impact performance. And we want to understand what other things are happening that could impact performance. Now, before I go on to that section of this presentation, I'm going to show you it's the exact same script I ran, and I allocated 1,000 nodes, but I didn't read as much data. I went against a subset of the data set. And let's see if the tooling catches what I did, right? So this job ran for 24 minutes. Remember, same script, just a subset of the original data, and same number of parallelism, ADLAUs. Already there's a warning, and it says one issue found, view in the diagnostics tab. I'll go to the diagnostics tab, one issue found, click on resource usage, and look at this. We've caught my mistake. I've allocated 1,000 nodes, but look at the red line. It's way at the bottom. This is clearly indicating that I'm wasting the vast majority of those nodes for the runtime of the job. Okay, so that's the demo. Let's try to understand now how performance and query execution actually happens. Okay, we've concluded the demo now, and we've seen the job graphs. Let's take a look at what it all meant. So we have to start from the store. Now, Azure Data Lake Store can store very large files, from kilobytes to petabytes. Now, those files are chunked up, okay? And those little chunks we call extents. And the size of them is not so important. It's megabytes or more. The size can vary. And the key thing is, for each piece, the piece is triplicated and scattered across our cluster so that if one machine goes down, we can replicate it and bring back the copy. So it enables a very reliable file system. And on top of it, when you split apart a big file into these pieces, it enables two interesting features, which is parallel read and parallel write, which are really the foundations of performance in a big data system, parallelization. Now, as a small file, let's say 100K, it's only going to occupy one extent, and you can probably imagine only one vertex. As a file gets bigger, there are more extents, and you can have more vertices for the extent. So that's the simplest way you can parallelize things. The file can grow, or you can have multiple files. But let's take a look at a very simple file. Pretend this is a CSV file or a TSV file, and it came from a search engine like Bing. And all it does is we have people who've been typing and searching for things, and they've gone to in their session 3, 1, 2, and in those sessions they clicked on different domains in the results, and we've counted the clicks. Now, you have to pretend that this file is not the small number of rows I have here, but billions of rows. So when you've written this file, and this file was in parallel written by multiple machines, the sessions are all over the place, because maybe you went through our front end and one server wrote the log here, you went the second time a different server, so you don't know where all the Facebook records are. You don't know where all the White House records are, or the CNN records. They're sort of scattered in all the extents, okay? And we were interested in counting by domain. So you can see the key, which is domain in this case, are just everywhere. So if we want to do anything about the domains, like how many clicks per Facebook, we have to look at all the extents. We have to read all that data. Now let's look at the right. Let's suppose I could just hypothetically force all the Facebook data onto one extent and all the whitehouse.gov data on one extent and CNN. It's a very different layout. You can see just how the colors lay out, right? The data is close together, and this enables a lot of performance improvements, which we'll show. So by the way, how did I create that structured data? Well, I created a USQL table. Syntax is very, very simple, and the first one creates the table and defines it. The second statement, the insert into, fills it with data. The red part is the one that you should focus on. It's creating an index, and what it's saying is clustered by domain ascending. The key parts there are clustered and domain. It means bring the nodes with the key domain with the same value together. Bring the Facebooks together, the White House, the CNN, try to put them on the same extent if possible. So now there are two scripts on this screen. On the left, it's how to read from just a pure text file. On the right, it's the same data, but in a table. So at the bottom, the script is the same. It's the red parts that are different. As you can see, it's very simple to read from a table. You just do select star from the table. Now, what happened performance-wise? On the left is, remember, CNN could be anywhere. We don't know. So all the extents have to be read, and then you have to filter for CNN, and then you have to write. Okay? Look what happened on the right. We want all the rows with CNN, but hey, we know where the CNN records are. So we don't even bother reading the extent 1 or extent 2. We just read extent 3. This is something called partition elimination. Very important for maintaining high performance on big data sets. Partition your data correctly, you can simply eliminate a large number of I/O operations. Okay, let's try now aggregating something, right? And in aggregation, we're going to do select domain, and we're going to sum the number of clicks by domain. Okay, very simple script, and we're grouping by domain. Let's take a look at what happened. On the left with the file, again, well, the extents of the CNN, Facebook, White House are everywhere. And so if you imagine we have 3 vertices, on each node we can compute a partial aggregate, but we have to bring all the partial aggregates for CNN, Facebook, and White House together, and that's that crisscrossing lines, which is called shuffling. And later on we can parallel write the results, but the crisscrossing is I/O. And the crisscrossing being I/O means it's a very expensive operation. This job will be slow, right? Especially as the data gets larger and larger, because every node has to shuffle data. Look what happened on the right. You can already tell there's no shuffling, right? Each vertex on each extent can simply read, aggregate, write in parallel. The thing happens very fast. So this is how data partitioning really has a big impact on USQL performance. Now, it should be clear how these graphs work now. Why did the graph go low? I was probably doing an aggregation. Could we speed things? Could we get things more parallel? Let's partition our data some more. So now you understand what's happening with the USQL query as it's submitted, as it's compiled, how vertexes run, and how to think about the key performance issues that affect a USQL script. So my call to action, first, go to our data lake site. That link is to our GitHub. You can find links to everything, every resource in MSDN or Azure.com, and where you can send us feedback. But please sign up for the service. Please use it, and then give us your feedback, what you liked about it, what you didn't like about it. We're really curious. If you don't want to spend the money to run the service, and you just want to play with USQL and learn it, because it is, frankly, quite a fun language, you can at least just download for free Azure Data Lake Tools for Visual Studio, and you'll need a Windows x64 box for this. You can run USQL scripts locally on your own text files, on your own machine, and you don't have to pay us anything. Learn from USQL, tell us if you like it or not, send us feedback. Thanks for your time.